In these slides, we will be introducing collaborative filtering, and we will first present one type of this approach, which is called user-to-user neighborhood approach. So, collaborative filtering is currently the most well-known approach to generate recommendations. And this is in large part due to the successes it had at the Netflix Prize. We will be talking more about the Netflix Prize a bit later in the course. Collaborative filtering has a unique characteristic that it only depends on the interactions of users to items, on the feedback that users give to specific items. And in some sense, collaborative filtering tries to find patterns from these interactions to exploit, if you will, the wisdom of the crowd. A distinguishing feature is that it requires no item content. No content information is necessary about the items. This is, of course, in contrast to the content-based approaches for recommendations. And because no content information is required, we say that collaborative filtering is domain agnostic. It does not care about what kinds of items are being recommended. Collaborative filtering only uses information from the interactions of users to items. In these slides, we will be focusing on explicit feedback, so we will be talking about ratings. So collaborative filtering, to be able to work to extract patterns from these user to item interactions, there must be some assumptions made. So the basic assumption is that the behavior of users, as expressed by their ratings, is completely guided by their preferences. There is a set of preferences that somehow remain relatively stable over time and consistent. This means that we can expect to see similar behavior from a user as the user has done in the past. Moreover, if we look at two users which are considered similar, we can expect them to like the same or similar items. Collaborative filtering can be generally classified into two main classes. The first is called the memory-based methods. And they are called memory-based because they essentially need to remember the entire history of the user-to-item interactions. Members of this class are the so-called neighborhood approaches that we will be discussing, specifically the user-to-user and the item-to-item approaches. The other big class are the model-based methods. Instead of remembering the entire history, these methods build a model that describes the history, and then use that model to make recommendations. A typical example of this family is the matrix factorization, and these methods are typically considered the most well-established techniques of collaborative filtering. For the remaining slides, we will be talking briefly about some history of collaborative filtering and then introducing the user-to-user collaborative filtering technique. Then we will be talking about item-to-item approaches, how to deal with implicit feedback, and how to address cold start problems. So let's start with some historical facts. The term collaborative filtering was first introduced in the context of the Tapestry system at the Xerox PARC Research Lab. So this system was used to manage emails from newsgroups and mailing lists. And the goal of the system was to identify filter emails that were supposed to be interesting to the user. So far, a user had some available options, and these were mainly to subscribe to mailing lists, for example, according to a topic, or to specify criteria that an email must satisfy in order to reach their inbox. And this was the conventional filtering. This image here comes from that work and attempts to illustrate the benefits of using collaborative filtering. So the top left figure is there is no filter whatsoever. Top right shows that there are some distribution lists, but still these are not enough. The user is overwhelmed with information. Conventional filtering does some filtering on top of the distribution lists, but this filtering is considered not to be ideal. What we would like to have is a situation where the user is only shown emails that are of interest to him or her. So, how does the tapestry system work? First, and this is the distinguishing aspect of the system, is that it is able to record the user interactions with the emails. The items here are the emails. And these interactions can be explicit in terms of ratings. For example, this email was interesting to me. Or it can also be implicit feedback. For example, a user has replied to this email. Based on all these recorded user interactions, users are then able to do collaborative filtering. Filter emails based on these user interactions. So, for example, I can say that I only want to see emails to which John has replied to. So, an important thing to notice is that Tapestry was not a recommended system, so it was not actually giving you recommendations of emails to read. As following this basic idea of Tapestry, which is to record the feedback of users to items, the groupless system provided some additional functionality. So as we see here in the figure, when presented with an email, the user could then decide to rate this email on a scale of 1 to 5. The distinguishing characteristic of the groupless system compared to Tapestry was that it was trying to predict the rating a user might give to a specific email. Okay? And this predicted rating is then going to be used to prioritize the emails a user sees. The specific approach that was introduced for this goal is a user-based collaborative filtering, which we'll be discussing later. So let's try and see the first collaborative filtering approach. It's the user-to-user collaborative filtering. Before introducing the user-to-user collaborative filtering approach, we need to specify some notation that we'll be using throughout the slides. We have a set of users U, and the number of users is typically denoted as M. We also have the number of items, N, and we have ratings. Ratings are the explicit feedback of a user to an item. So we denote R and subscript U, I to indicate that this rating was from a specific user to a specific item. The values it can take are in some domain, say 1 to 5 stars. In collaborative filtering, we would like to predict the rating of some items that the user has not rated. So we write the R hat to be the predicted rating or the score of S of U, I. So this is for a pair of user item that we have not seen before. U is typically called the target user and I is called the target item. So when we talk about predictions, we have a specific target user in mind and a specific target item in mind. In collaborative filtering, all you have to work with are the ratings of users to items. These ratings can be organized into a matrix where rows represent users and columns represent items. In the matrix shown on the right, we draw as gray those cells which correspond to observed ratings. White cells mean that the system has not received any rating for that particular user item pair. Typically, the number of gray cells is much less than the number of white cells. We say that the ratings matrix is very, very sparse. As an example, consider a dataset that is commonly used for research in recommended systems. The MovieLens 20 million dataset has about 30,000 items and 140,000 users. Among the almost 4 billion possible user-to-item pairs, the system knows only 20 million ratings. This represents 0.5% of all possible ratings. I hope you see the challenge with such sparse ratings matrices. The system essentially needs to guess or better predict the large number of unknown ratings in order to make recommendations. Generally, in collaborative filtering, the goal is to predict the rating of a target user to a target item. In the user-to-user collaborative filtering approach, which is also called user-based neighborhood collaborative filtering, the main idea is to identify similar users and then combine their ratings. The intuition is that if like-minded users like a movie, then you are most probably going to like it as well. This comes from the basic assumption of collaborative filtering. In user-to-user collaborative filtering, there are 3 questions to answer. First, what do we mean by user similarity? How does the system capture it? We will introduce a similarity function for that purpose. Second, which users should the system consider to be similar to the target user? This is the neighborhood selection step that determines who affects whom. Third, how are the ratings combined? What is the prediction formula used? We note that there are different ways to answer these questions. Here we will only provide some indicative answers, leading to approaches that have been shown to work well in real-life cases. We will introduce user-to-user collaborative filtering progressively, starting from a simple idea and building on top of that. Specifically, we will talk about a non-personalized approach, then we will make it personal, remove some biases, and later we will introduce the user similarity functions and show their role. First step, we want to make a non-personalized rating prediction. Non-personalized means independence from the target user. Every user will see the same recommendations. So what is the simplest approach we can think of? Predict the rating of an item to be that item's average rating. So this is shown by the formula here, where UI is the set of users that have rated I. How can we tell that this prediction is not personalized? If we look at the formula, the prediction does not depend on the target user U. Let's now try to make a more personal prediction. Most likely, the target user is not like the average user. The preferences of the target user may be more similar to some users and very dissimilar to other users. So how can we consider this observation? Assume we have a magical way of quantifying users' similarity. Specifically, we know a weight W that expresses the similarity between users U and V. For the time being, let's not focus on how we know such weights. The similarities take value ranging from 1, meaning complete similarity, down to -1, meaning complete anti-similarity. Essentially, -1 means that the two users give totally opposite ratings. One gives 5 star, the other gives 1 star, and vice versa. So in this range of -1 to 1, what does a weight of 0 indicate? It means that there is no connection, either positive or negative, between the ratings of the two users. We cannot tell something about user U by looking at the ratings of user V. Okay, so let's use these given similarities. Instead of the average rating, we will compute the personalized to the target user weighted average. The weights are the given similarities. The predicted rating formula is now shown. The sums are shown over all users, but in practice we sum over all other users who have rated the item. Note that the sum in the denominator uses the absolute value of the weights. Why is that? Because we have negative weights. Okay, so what happens with a negative weight on the numerator? A negative weight essentially reverses the rating given by the other user. If the other user did not like a movie, the target user will probably like it, and vice versa. In the formula shown here, we assume that the ratings take both positive and negative values, that is, go from -1 to 1 for this to work. So we've now made the predictions personal, but we must account for rating bias. Users might have different interpretations and uses of the rating scale. I, for example, tend to be very positive, and I only give bad movies a 3-star rating out of 5 stars. You, in contrast, can be less forgiving, and you are using the entire scale. So a rating of 4 might have a different meaning to different people. How can we account for these differences? An apparent solution is to normalize ratings, and the simplest way is to subtract the mean. The intuition is that a better indication of users' preference is how far a rating is from the user's personal mean. For example, if my mean is 4, then a rating of 4 is a rather weak endorsement. Whereas if your mean is 2, your 4-star rating is a very strong endorsement. Let's put this idea in practice. Instead of raw ratings, we will predict rating deviations. You can think these deviations as normalized ratings, where we follow the normalization principle of centering around the mean. For the prediction formulas, we just need to replace the ratings with rating deviations. This way, we are predicting the deviation for the target user. We still need to add back the mean rating of the target user in order to recover their predicted rating. The updated formula is shown here. There is one small thing to notice here. Predicted rating can now go outside the rating scale. For example, if my mean rating is 4 and all other users give 2 stars above their average for a specific item, then my predicted rating becomes 6. This is not a problem if you want to rank items by their predicted rating. In that case, the relative order only matters. In any case, you can simply trim the predictions to fall in the desired range as a final step. Now it's time to talk about those magical weights measuring user-to-user similarity. Let's see how we can compute them. Again, there are different ways to do that. Here we describe one that works well in practice. Recall what we want from a similarity. 1 means complete similarity, 0 means no similarity, and -1 means complete anti or opposite similarity. The gold standard is to use the Pearson correlation coefficient with a small change. This is closely related to the mean-centered cosine similarity, as we will see. Let's give the intuition for the Pearson correlation coefficient, or for short PCC. Any correlation measure captures the degree to which two series of numbers agree. In our case, the numbers are the ratings. Correlation increases with the frequency of agreement, for example, when we like and dislike the same movies. Correlation also increases with the intensity of agreement, for example, when we strongly like or hate the same movies. On the other hand, correlation is weak, close to 0, when there is no clear agreement pattern. Here is the formula for the PCC of user U and V. Let's see first what the numerator computes. It looks at each common rated item and sums a term. This term is the product of the rating deviations of user U and V. Let's examine this product in more detail. If both users agree with positive deviation, say +2 stars, then the product is a positive number, 4. If both users agree with negative deviation, say -2 stars, then again the product is a positive number, 4. Now if the two users disagree, one says +2, the other says -2, the product becomes negative, -4. If we sum up all these products, we get a measure of agreement or disagreement between the users. If there is no pattern of agreement or disagreement, the terms are sometimes positive, sometimes negative, and thus some close to 0, meaning no correlation. The numerator plays a normalization role. It sums over all items rated by each user independently and results in the coefficient taking values in the range of -1 to 1. Let's see an example of computing PCC. Consider the ratings of a user represented as a vector. It helps to think of this vector as a row of the ratings matrix. We show here two vectors containing the mean-centered normalized ratings, that is, the rating deviations. Each user, U and V, has rated only 3 items. For the first gray item, both users agree with a positive deviation, resulting in a positive product of +2. For the second gray item, the users disagree, resulting in a negative product of 0.5. In the last gray item, the users also agree, this time with a product of 0. So overall, the total agreement is positive. It's 1.5. We then have to normalize the total agreement, and we compute the standard deviation of the two rating vectors. We multiply them, and in the end, we get a PCC of 0.55. This is quite high, indicating that the two users tend to agree in their ratings. We make a small note on the formula we used for the PCC. This formula contains a slight change from what the definition of Pearson correlation is. Normally, you would consider the common rated items both in the numerator and in the denominator. However, there's a bunch of problems when using the common items to normalize in the denominator. For once, if the users have just one common rated item, the users are perfectly similar. Clearly, this is not what we want. Another problem is that with only two common items, the users are again perfectly similar, either positively or negatively. In general, if there are only a few rated items in common, the similarity tends to be high. For example, consider two users that have rated 100 items, but only 10 of them are commonly rated. Do we really want their similarity to be determined by the similarity in those 10 items and ignore the fact that there are 180 other items that they have not rated in common? So this is counterintuitive. And for a while, there were various approaches proposed to handle these problems. It turns out that the simplest one was the most effective. So we normalize by all items and not only the common items. This way, if two users have a lot of uncommon items, they are no longer considered similar. Another note about the PCC is its relation to the cosine similarity. To see this, consider the ratings vector U for a user U containing mean-centered ratings, that is, the deviations. If an item is not rated, then the vector contains a value of 0. Let's now see how to compute the cosine similarity on such rating vectors. The cosine similarity is the angle between the two user vectors and is computed using the inner product of these two vectors. Because the vectors are mean-centered, the cosine similarity gives the same score as the PCC formula we used before. To see this correspondence, consider the previous example. Green is the formula for PCC and yellow is the formula for cosine similarity. Observe that the numerator in PCC is essentially the inner product of the two vectors. Also, observe that the denominator is the product of the norms of the two vectors. Let's go back to the rating prediction formula. We have just shown how to compute the similarity weights W using the PCC or equivalently the cosine similarity. We make one last change in the formula. Currently, it considers all users to make predictions, including those who are not really that similar. That is, they have a similarity close to zero. This may introduce noise to the prediction, which we want to avoid. A standard solution is to limit the set of users in the sum to a small neighborhood of users who we expect to be more useful in predicting the ratings. We denote as n of u the neighborhood of target user u. So the prediction simply changes to the weighted average deviation in the neighborhood. This is also the reason why this user-to-user approach is also called user neighborhood collaborative filtering. Okay, so who goes in the neighborhood? We would like to have users with high in absolute value similarity to the target user. There is no reason to exclude a highly similar user in favor of a less similar user. Note that in practice, the neighborhood only contains users who have rated the target item. A few more notes on neighborhood selection. Generally, there are different ways to choose the neighborhood, all being valid, but serve different purposes. Here we list a few. In the extreme case, we can include all users. This is a valid neighborhood. We can only take the k most similar users. We can set a similarity threshold and then get only users above that threshold. Then there is the question on whether to include users with negative similarity so as to learn what not to recommend. A gold standard is to include a fixed size neighborhood of maybe 25 to 100 users. This concludes everything about the user-to-user collaborative filtering. Let's see how we can make recommendations to a specific target U. First, we need to compute the similarity of the target user to each other user using the PCC. Then, we create the neighborhood of the target user by selecting those with the highest PCC, perhaps in absolute value. Next, we predict the rating of each item that the target user has not rated using the formula shown here. Finally, we recommend the item or the items with the highest predicted rating. Before concluding the discussion on user-to-user collaborative filtering, we make some notes on its computational complexity and sketch some optimization ideas. We measure in terms of the number of users m and the number of items n. The former is typically in the order of millions, while the latter is in the order of thousands. So, computing the similarity between two users is order n, as we need to compare at most n items. Computing all pairwise similarities takes m squared as much time, giving us an order of n times m squared. Creating a fixed size neighborhood takes order m time. Rating prediction, given the neighborhood and the similarities, is linear on the neighborhood size k. And finding the item with the highest predicted rating is linear in the number of items n. So the most expensive operation is computing user similarities. Let's see how we can make neighborhood creation faster. Consider the target user shown in the ratings matrix as the yellow row. This user has rated a few items shown as green columns. When computing similarities, we only need to look at other users that have rated at least one of these items. These users are shown as red. Let's now see how we can optimize the recommendation phase. Again, the target user is shown in yellow. The neighbors are shown in red. The possible items to recommend are those that are rated by at least one of these neighbors. These items are shown in green. So we only need to predict the ratings for these items. Before concluding, let's discuss some potential problems with user-to-user collaborative filtering. As we said before, the known ratings are very sparse. The densities can be as low as 0.5% or in the Netflix dataset about 1%. As a result, it may be possible that two users have not rated any item in common. Thus, similarity cannot be computed. Another issue is computational performance. As we said, the most expensive part is the pairwise user similarities, which is quadratic to the number of users. As the number of users can get in the order of millions, this is a serious problem. Moreover, pre-computing similarities and neighborhoods does not help. User similarities may change a lot as new ratings come. Think that if I only have a few ratings, one additional rating carries a lot of weight. So this concludes the user-to-user collaborative filtering. Some ideas for these slides come from a specialization course in Coursera, Recommender Systems.